Okay, so in the last video here, we're going to pick up where we left off. We had come up with this expression for the electric field in the x direction, and we ended up with this integral here with some constant stuff out in the front. Okay, so what we're going to do to solve the integral is we're actually going to kind of cheat in a way, and we're going to look up an integral from a table, and we'll use it to evaluate the integral. So this is something that people do all the time, engineers and scientists, and sometimes the integrals would require so much work to solve that it's really not worth it for the purposes of learning electricity. So we're just going to take a shortcut, and this is the integral that I found in the table. Now the variables in this integral are not the same as the variables in my problem, so I just have to kind of match them up. And so the integral table tells me if I evaluate this expression, I should get this. So I am not going to show you where that comes from. I'm simply going to provide this from a table. If this was a test, I would give this to you, or the AP test would give it to you. So don't worry about going from here to here, okay? So the next thing I'm going to do is I'm going to write down an expression that should match this. Half. Okay. And I'm going to leave it up to you to verify this, right? This is basically matching up table variables with the other formula. So this is a good exercise for you to make sure that that's right. Okay? And then I'm going to evaluate here. This is a definite integral, so y goes from negative a to positive a. Okay, so this is a little bit of practice with integrals and evaluating definite integrals, because your next mission is to write this expression out, subtract those terms, and simplify. Okay, so you guys should be able to do this. I'll work it through. We've got kxq over 2a in the front, and then my terms are going to go like this. Now, that would be a good thing for you to pause the video on and try it and see if you agree. Because if you don't, you got to practice a little bit with your algebra in solving definite integrals. Okay. Notice I'm subtracting a negative here. That's not a mistake. That's on purpose, right? That's how you evaluate definite integrals. Notice also I'm squaring a negative here, which of course doesn't make any difference at all. But now, next thing, again, I would recommend you do this on your own and then verify. I'm going to bring terms together, simplify. Okay, again, I really highly recommend that you go from this step to this step and then come and check your answer to make sure you've got it right. You have to be able to do these steps correctly. Okay. Then I notice that 2's are going to cancel out. I also notice that a's are going to cancel out. And I am pretty much done. And I have an expression now that is my final answer. Okay. So I've kind of reached my goal here. I've solved the expression. I now know that the electric field at point P, a distance x away from the charge line, is going to be equal to this expression, which has the total charge built into it, the total charge on the line, and it also has A in it. Remember, A is the half length of the line. So I mean, common sense-wise, if you have more charge on the line, a bigger Q, you'll have a stronger electric field. Also common sense, If you're further away from the wire, like X is bigger, field is smaller. And if A is bigger, meaning you spread the charge out more thinly, then the electric field will get smaller. So in other words, increasing X or increasing A will decrease the electric field. Increasing Q will increase the field. So they have the opposite effects. So that kind of makes sense. Okay. If you want to be really complete, let's go back to our original expression, and now you can say that that term goes in front of the I hat, and I'm just going to write 0 newtons per coulomb in front of the J hat. So that's really my complete answer for the net electric field. Okay, that's it. Okay, so there we have it. Lots of steps. I highly recommend reviewing and trying this again on your own, seeing if you can do it. I'm going to show you one other thing here in this video, and then that will be it. I want to come back to our question about what if the line was infinite? What could we do? And it's pretty easy to show you with a limit what happens. Okay. So now we're going to extend the line, and we're going to be careful to be adding charge as we go to maintain lambda, right? So if you want to stretch the line out to infinity, that's fine, but make sure that you're also adding charge as you go. Otherwise, the charge will spread out to nothing. Okay. So the total charge that we're going to have is going to be equal to lambda times 2a. Okay, and that's fine. So I'm now going to write, I'm going to write my expression from before. E is equal to k times q over x times x squared plus a squared to the 1/2. But for q, I'm going to write this. So I'm going to just plug that in. Okay. So that's important, right? Because if I'm making a longer, I'm also increasing q. So this is a very important thing to substitute here, the fact that there's an a built into it and a lambda built into it. Okay. So now let's simplify this. We've got 2k lambda a. All right, and down here, I'm going to do a little bit of tricky stuff. I'm going to write x out in the front, and then I'm going to factor out an a squared. I think you're going to need to convince yourself that this expression down here is the same thing as what I have up there. You know why I'm doing that? In math class, remember when you take limits, you like to sometimes get the thing that's going to a very large number to be in the denominator. So remember, we're going to make a really big. So if I can get a squared down here in this denominator, I know this term is going to go away. So we're kind of anticipating that here. So now let's do more. This 1/2 acts on this a. And what's going to happen is that that's going to come out, and it's going to come out here. Right? Laws of algebra. The 1/2 x brings this out. And then this a is going to cancel with that a. And I'm left with 2k lambda all over x times 1 plus x squared over a squared. I just flip those terms around to the 1/2. So again, your eyes might be rolling back a little bit because of all the algebra, but all we're doing is what you would do in math class when you're finding a limit. We are anticipating that a is going to be much, much bigger than x, and so we wanted to put it we wanted to put it into the denominator. Okay. So now we do a limit. Limit is a is much, much bigger than x of that expression. I'll just write it both. Right? And what you'll find is that when a gets really big, x squared over a squared, that's going to become 0. Of course, 1 doesn't go away, and so what you're left with is this expression 2k lambda over x, because that x hangs around. Okay, so this is going to be the electric field when a is much, much bigger than x. And that, in fact, is what we wanted to get at the very beginning of this derivation, is to find out how that electric field varies. So now we know that it's going to be 2k lambda over x. What's significant about that is the fact that the electric field gets weaker as you get further from the line, and it gets weaker in an inverse sort of a way. So it drops off as 1 over x. And we are going to spend a lot of time talking about the implications of that and doing examples of problems and applications. So I'm going to leave it there for now. I think that's enough, and we will talk on this stuff when we get back to class. See you later.